So when we started talking about energy, the first form of energy we introduced was kinetic energy, which was energy due to the motion of an object. So we said if you take a block, put it on an inclined plane, and that block slides down the inclined plane, there's some kinetic energy that we're going to want to keep track of due to the block's motion down the inclined plane. We calculated that out by saying that the kinetic energy due to the motion of an object is equal to 1/2 mv squared, where m is the mass of the object and v is the object's speed. And that was true for the motion for anything that we were modeling as a point particle. But of course now we're treating things as rigid bodies. And of course a rigid body has more than one type of motion that it can undergo. So if I take a sphere and now put it on that same inclined plane, put a ball up there, not only will the center of mass of the ball move, but the ball itself will rotate about that center of mass point. So what I have now is I have two types of motion that I need to describe. And so the first of these, the kinetic energy due to the motion of an object's center of mass, that is what we've been dealing with. That's our 1/2 mv squared. We're just going to relabel that as the translational kinetic energy. That's the kinetic energy due to center of mass motion. The second type of motion we can have is kinetic energy due to an object's motion about its center of mass. So this is rotational kinetic energy. And again, notice what we've done here is we've taken our translational quantity and replaced it with its rotational analog. So mass becomes moment of inertia, speed becomes angular speed. And so our rotational kinetic energy we're going to calculate as 1/2 times the moment of inertia of the object times omega squared. And of course the moment of inertia cares about the axis. What we'll see is that for many problems this will be about an axis through the object's center. But there are going to be situations where we can treat all of the motion as rotational motion about some pivot point that's not at the object's center. So of course this really matters when we start thinking about using the work energy theorem or our energy balance equation to work a conservation of energy problem. And so when we set up conservation of energy initially, we said, well, looking at this equation, what types of energy do we need to keep track of? And we said, hey, we're going to start by keeping track of kinetic energy, energy due to an object's motion. Well, now we said, of course, there are two different ways that an object can move, and we need to keep track of both of them. So we're going to reframe this question to what types of kinetic energy do we need to keep track of? The first one being translational kinetic energy, energy due to a motion center of mass. So the question we're going to ask ourselves in terms of determining whether or not we need to keep track of translational kinetic energy is, does the center of mass of the object move? If the answer is yes, then we want to keep track of translational kinetic energy. The second type of kinetic energy we need to keep track of is rotational kinetic energy. Again, this is energy due to the fact that a rigid body can now rotate about its center of mass. The question here is pretty straightforward. Does the object rotate? Yes or no? If the answer is yes, then we're going to keep track of rotational kinetic energy. Again, everything else is the same. So how do we keep track of the work done by all the forces? Well, there are two potential energies that we're going to use to keep track of the work done by our conservative forces. So the gravitational potential energy, the elastic potential energy. We'll determine what the 0 point is going to be for those potential energies if we need to use them, and then figure out what the potential energy is initial and final relative to that 0 point. And then the work done by any other force is still going to get grouped into this work done by non-conservative forces term. So the only thing that's really changing here is that now when we think about the initial kinetic energy, we have two kinetic energies that we want to think about. Just like when we've dealt with the potential energy at this point, we've said, well, there are two potential energies that we need to think about whether or not we need to keep track of. So what we've got is we've got basically four two kinetic and two potential energies that we're going to determine whether or not we need to keep track of, and then everything else, the work done by all other forces, is going to get lumped into that work done by non-conservative forces term.